Hey everybody, welcome back. So last time we talked about the three different properties of light, the frequency, the wavelength, and the energy. And we talked about how even though light has these three properties and they may differ in the amount of energy, it is all light. There's no fundamental difference between gamma rays and radio waves, except for the fact that they've got different energies. So even though your eye isn't sensitive to seeing radio, for example, it's still light. There's no real difference between that. So in this lecture, what we want you to see are what effect does that energy have on the different types? And so what does that give us that we can use these different types of light for? So we mentioned that all light is part of the electromagnetic spectrum, and you're going to hear me abbreviate this to the EM spectrum because electromagnetic is too many letters to say, and we are all lazy here, right? So this is all of the different types of light that we've talked about so far: radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. And this gives you an idea of the wavelength. You worked with this in the practice from the last one. And then some comparative sizes for here. Now radio continues all the way on to infinity. Same thing for gamma rays. So radio gets longer and longer and longer wavelength, and gamma rays get shorter and shorter and shorter wavelength. So the shortest wavelength radio waves are about the size of a building. But again, by the time you're getting up to FM band, you're looking at about the size of a mountain, and an AM may be the size of the United States. Microwave's about the size of humans, as you can see. And then honeybees and needles, and by the point of the needle, we're talking about actually this point right here. By the time you get down into visible, you're getting down into just tiny, tiny little nanometer size things. All right, so let's look at each of the different types in particular. Now, visible light is what you're mostly familiar with. This is what makes up, if we break this up, this becomes the colors of the rainbow. And if you've never seen a rainbow, get a life. There's actually only 6 colors in the rainbow, and you may have heard red, orange, yellow, green, blue, indigo, and violet. Indigo is a color, yes, but it's only in the rainbow in the same sense that pumpkin or sunset or chartreuse or any of these other colors are there. There's really only 6 colors that you can distinguish, and that's going to be the red, orange, yellow, green, blue, and violet here. You can also call it purple, that's fine. And the reason why they came up with this 7 colors because when we first started studying light in the 1500s, 1600s, there was still a lot of mysticism in science. Light is directly from God. The only perfect number is 7, so there must be 7 colors. So I see indigo. Yeah, that's that ticket, but it's not really there. So next time you do see a rainbow, go out and take a look at that. Now, the only reason why we think visible light is special is because that happens to be the light that your eye is evolved to be able to see. And the reason for that, and you're going to see this later on, is that the sun puts out most of its light in the visible range. So your eye evolved to take advantage of that. If our sun put out most of its light in infrared, and there are stars that do that, then your eye would have evolved to see in infrared. So that's basically how it works. Redder than red, a light so red that your eye can't see it, is infrared. And you're probably familiar with this. I mean, your eye can't see it, but your skin perceives it as heat. And so that's what we've got down here. This is a heat lamp that's shining down. And so you can feel that light. And yeah, you can see some red there, but most of the light that's coming out is actually in the infrared. This is a military night scope. Infrared is not green. Don't get confused by that. What the night scope is doing is that it's sensitive to infrared. It detects that, and then the computer inside changes that into a color that your eye can actually see. The only reason we use green is because it won't destroy your night vision. So that's the secret of what we're doing with that right there. You're probably even more familiar with something like a remote, something like this. The way the remote talks, there's a little light bulb right here. I'll put that up where you can see that. That's actually sending out infrared light. And if I were to flash this at the screen after I turn off all the lights, you can actually see this light up. So that's something I'd like you to try. Most of your webcams are actually sensitive to infrared. And so I can't turn off the light here because it would mess up my recording. But if you do this at home, turn off all the lights in your room, and then your webcam, which is probably sensitive to infrared, just take it and then flash the remote at the webcam, and you're actually going to see that light up from that. Even though right now, when I push buttons on this, you can't see it at all. So the infrared light is coming out of the remote and shining at the camera or whatever particular instrument that you're using, and it flashes in a code. And the code of those flashes is what's telling your device to do whatever it is that you want to do. So even redder than red, even redder than infrared, is a microwave. Yes, that expensive microwave oven that you've got sitting on your countertop is nothing but a big red light. It's just so red that your eye can't see it. And what's special about microwaves is that microwaves have a wavelength so that when they pass through water, it causes the water molecule to start rotating. And if you know anything from chemistry from high school or whatever, anytime I have a molecule that starts moving faster, that starts vibrating faster or rotating faster, that's an increase in temperature. So this is how the microwave's cooking your food. It's actually using the water in the food to boil it. So anytime you're eating something out of a microwave, you're eating food that's been boiled. Lovely. So this is also why if you put a hot dog in the microwave, then when the water inside the hot dog starts to boil, there's a limit to how much force that skin of the hot dog can take. And eventually it ruptures, and this is why things explode in the microwave. Even redder than microwave, the reddest light of all is radio. And as I said, radio goes on and on forever. It's the longest possible wavelength. Lots of different bands. We talked about the FM band, the shortwave band, the citizens band. All these different types are really just different wavelengths of light that's coming in. We also use it in radio astronomy because, as you can see in the picture here, and we'll be doing some work with this later on in the semester, but this is actually a galaxy right here. And if you just look at it with a telescope, that's all you see. But if you look at it with a radio telescope, you can see that it's ejecting an immense amount of material out to the side. And that's something you can't see in visible light at all. So looking at things in radio is actually teaching us a whole lot about how these active galactic nuclei form. It turns out this is actually a black hole that's going on. So radio has a very long wavelength that can penetrate the atmosphere very easily, and so this is why we use it for communication most of the time. But it also has a very low energy. And so because the energy is low, you're getting bathed in radio waves all the time. Now, you may have heard that cell phones cause cancer, for example. Well, cell phones are using radio, but let's think about it. Which has more energy, radio or visible light? Well, okay, if the visible light has more energy, then you're doing more damage by taking a flashlight and putting it to your head and turning it on. And that's a really ineffective form of suicide when it comes down to it. So that radio is not going to hurt you. There is actually no way that you can get cancer from listening to cell phones and things like that. So flip over on the back page. If we go the other direction, we go bluer than blue, the first kind of light that you get is ultraviolet. Now, again, your eye can't see it, but your body can detect it, and that's what's happening down here. This is what turns you sunburned, or some of you lucky people actually get suntan, but not me. So there are actually species of butterflies that you see here where their spots are colored in ultraviolet. You can't see them, but the female butterflies can see them, and this is how we get baby butterflies from that. If you've ever seen a black light, then a black light is putting out most of its light in ultraviolet, and that ultraviolet can make, like pigments in your shirt glow and things like that. That's what gives it all its kind of funky properties from that. Now, interestingly though, this is actually a range. Some people can actually see slightly into the ultraviolet. Some people can see slightly into the infrared. We discovered this actually in World War II, that there were some people who could see ultraviolet. And so we thought, hey, this would be a great idea. We'll light up runways with black lights. That way, the Germans couldn't see that. They couldn't bomb our airfields, yet our pilots who could see in ultraviolet would still be able to land. So we did some research, and we found that people with ultraviolet vision, the people most likely to have ultraviolet vision, have fair skin, blonde hair, and blue eyes. The entire German Air Force had fair skin, blonde hair, and blue eyes. So we figured, okay, this is probably not going to work out for us. But you may find that if you go into a party or whatever that's being lit by black lights, some people can actually see very well. They look around and go, oh yeah, this is fine. Other people feel like they're kind of stumbling around because they can't see very well. And that depends upon how far your vision goes into the ultraviolet. Even bluer than ultraviolet is X-rays. Now remember, the whole difference between these different types of light is their energy. X-rays have so much energy that they can actually penetrate your skin. And so they don't penetrate the bone. So when you're looking at an X-ray like this, what you're actually looking at is the shadow. So the X-rays pass through your skin and expose the film, but they're blocked wherever your bones are. And so this allows us to get a nice picture of what's going on inside your body from that. And by carefully calibrating the energy of the X-rays, we can determine how far it penetrates. So for example, if your doctor needs to get a picture of your lungs and the soft tissue that's inside the lungs, if he uses too much energy in the X-rays, it's just going to penetrate right through. But if he doesn't use enough, then it's not going to penetrate through your skin and maybe your clothes if you're wearing them. So part of the art of radiology is adjusting that energy to get exactly the different kinds of features that the doctor wants to see from that. Now, X-rays do have a lot of energy. You probably noticed that when the dentist is taking an X-ray, they're not going to stand here like you see this guy here. They're always going to step out of the room. Makes you wonder, do they know something that you don't? Well, okay, it has to do with repeated exposure to it. If you are repeatedly exposed to X-rays, it can actually cause damage to your cells. It can cause cancer, basically. But if you're just getting an X-ray a couple of times a year or something like that, there's nothing to worry about. It's not going to do enough damage to you for it to ever be a problem, unless you're pregnant. And of course, the fetus is going to be a lot more sensitive to these kinds of things. So if you even think you might be pregnant, you don't want to get an X-ray. But other than that, it's really not a problem. It's not something that you need to worry about. What you do need to worry about are gamma rays. Now, okay, probably not going to turn you into this guy, unfortunately. But gamma rays have a very short wavelength. And because they have a short wavelength and they have a high frequency, then they have a whole lot of energy. So this short wavelength is basically the size of your DNA or smaller. So when that energy comes into your body, it can damage that DNA in your cells. And when that happens, there's one of a few things that can happen to you. One, the organ can take so much damage that the organ dies, which ends up killing the organism. That's you. We call this radiation poisoning. Another possibility is that it can damage the cell in such a way that it triggers runaway growth. That's cancer, essentially. Another possibility, and this is actually fairly common because we're getting bombarded with gamma rays from space all the time, is it can change the DNA in such a way that it's not harmful. It doesn't have any real effect on the individual, but the traits that they pass to their children are going to be a little bit different from that. And this is the reason why we're not all clones of each other, is because we've all had these random changes in our DNA, and some have not had any effect, some have been beneficial, and so we get more people with that particular change in their DNA, some have been harmful, and so we get fewer like that. So when we're talking about X-rays, or gamma rays, these are produced in nuclear reactions generally. And like I said, we're getting bombarded with them in space all the time. They're the highest energy of light. Gamma rays are going to be produced by black holes. This is the inside of a nuclear power plant. The way the nuclear power plant works is that the gamma rays come out through the water and they heat the water, kind of like a microwave, but with much, much more energy. That water almost immediately turns to steam. That steam then turns a turbine, the turbine turns a magnet, the magnet produces the electricity, and that's how we get our power. So it's very, very efficient. Another thing that we use gamma rays for, though, is medicine. You've probably heard of radiation treatments for cancer. And you may think, well, wait a minute, if the radiation is causing the cancer, isn't that a problem? Well, what we do is we focus that beam very tightly so that the goal is to try to get it to shine directly on the tumor. And then we kill the tumor through radiation poisoning without, hopefully, killing the person who has the tumor inside them. This is why radiation treatments are pretty much always going to make you sick when you're doing that. Another possibility, though, I was diagnosed with something called Graves' disease, which is an autoimmune disorder. And so what happens is my thyroid would produce too much thyroid hormone, thinking that it was being attacked. And the more that the thyroid hormone it produced, the more it thought it was being attacked, and so you would get in this spiral. Well, thyroid hormone is what causes your cells to produce energy, so my heart rate was just through the roof. 50 years ago, I would have just died, because basically I would have eventually just had a heart attack from the energy levels ramping up. So when I went to see the doctor, he said, well, you've got a couple of choices. So we've got to get your thyroid out, and we're just going to use a replacement thyroid hormone pill for that. But somehow we've got to get your thyroid out. We've got two choices. We can cut you from here to here, and just have your head hanging off the table. Not quite that bad, but close. And then just scoop out your thyroid that way. The problem is that your thyroid's going to interpret that as an attack. It's going to produce this big rush of thyroid hormones, just like it was doing before, and there's a decent chance that you'll have a heart attack on the table and die right there. I'm like, yeah, not my first choice. The second possibility, though, he said, was the only part of your body that uses iodine is the thyroid. And so the waste from nuclear reactors, like we have down here at Palo Verde Nuclear Power Plant, produces radioactive iodine. And so he said, what we can do is we can have you swallow some reactor waste, some radioactive iodine from that. And then your body will take that up into the thyroid, and then the gamma rays from that will kill off your thyroid, and ideally just your thyroid. So I was like, cool. So, geek that I am, we recorded it. So what you're going to see in the video, I've got a Geiger counter that basically counts the amount of radiation. And if I were to just put this out in the classroom or whatever, which is what we normally do for in person, then you just hear beep, 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 beep. It's very just, slow, kind of casual thing, but that is basically the universe trying to kill you. So what you're going to see when we hold that Geiger counter up to the radioactive iodine is going to be a little surprising.
Okay, it's a big cup, little.
Okay.
Okay, that's what you're. Don't invite anybody over for apple juice at your house for a couple days, okay?
Yeah, I'm kidding.
All right, so I'm gonna hand you this pill. See, it's already gone crazy. Just taking it out of the lead. Here we go. Whoa.
And what am I going to do with this now?
You're gonna swallow it. Go for
That
it.
is seriously messed up. All right, here we go. Bottoms
Down the
up.
house, that's right. Woohoo! You are on fire, my friend.
Maybe she was in there.
I think we'll put this out of its misery now.
All right. Thank you, Dr. Wang.
Okay. All right.
Thanks, Doctor. Appreciate it.
All right. So what?
So, yeah, it was interesting. For about 2 weeks, I was too radioactive to be around other humans. So basically, I had to live in my house by myself. We had to cover all the furniture with sheets because my sweat was radioactive and all this other sort of stuff. And my wife couldn't come anywhere near me. My family had to move out of the house. I didn't feel anything. It felt all fine to me. Unfortunately, I did not seem to get superpowers. Still working on that one. But for a year, I had to carry around a letter from my doctor explaining what had happened because I would set off the radiation detectors in airports. So the gamma rays worked really well. They just basically killed off my thyroid. And now I take a little pill every day to replace the hormone it would have produced, and I'm good to go. It's not a problem. So gamma rays, yes, are produced in nuclear reactions and nuclear explosions even, but they also have a very beneficial medical effect that we can use for that. All right, so when we're talking about radiation, all light is radiation. Now, when most people talk about radiation, they're talking about gamma rays, because this is what makes the Hulk and the mutants and all that other sort of stuff. But all of this is radiation. There's no difference between the gamma rays and radio waves. The amount of damage that it can do to you depends upon the energy. So which of these types, look on your worksheet, which of these types of light then is the most harmful? Radio, visible, ultraviolet, or gamma? Pause the video and go ahead and circle it. Well, that's right. Gamma rays are going to be the most harmful because they've got the most energy. Ultraviolet rays are also harmful because if you get exposed to enough of them, they're still going to cause skin cancer. So this is why you need to be getting checked for skin cancer every year, from your head down to your toes. And yes, you need to get naked because these things can show up in areas that you would have never thought. Especially if you got sunburned much as a child, that's going to make you far more likely to get these kinds of skin cancer spots when you're older from that. So every year at least, go into the doctor's office. Don't let him just do, a screening where he lifts up your shirt and says, yeah, you're fine, or whatever. Make sure that you get checked everywhere because you can actually get skin cancer spots on the top of your head. You can get them on the bottom of your feet. You can get them on your butt. Anywhere that you've got skin, you can get skin cancer. And skin cancer is actually the deadliest form of cancer because once it gets into your bloodstream, you're probably going to die. The only thing that we can do is get in there and carve out all of the cancer flesh that's in there. And this has actually happened to me since moving out here to Arizona. And so they dug in about that deep, about that big around, and pulled that piece out. And man, that hurt. But it beats the heck out of dying. So go get checked every single year. Visible light, of course, you're used to, but then radio is not going to hurt you. It's not got enough energy that it's going to hurt you at all. You're getting bathed in this radio light from all the radio stations that are out there all the time. It's just not anything to worry about. All right, so that's it for this. Download the EM Spectrum Practice Worksheet from Canvas. That is going to look like this. It's basically just a matching, something that you can find for the different properties. I want you to learn these different properties. We're going to need those as we get later on in the course when we're talking about it. Okay, folks, so keep in mind, again, I'm going to keep stressing it, all of this is just light. There is no difference between radio and gamma other than the energy. And so that energy determines how it's produced, how far it can travel, what effects it has. In astronomy, if we were to restrict ourselves to just looking with a visible light telescope, we're only seeing a tiny sliver of the universe. So when we realized that these other types of light existed, that just literally opened up new windows on the universe. And particularly when you get into cool things like black holes and such, we're not actually going to be using visible light to look at a black hole. So we're going to need to know, how does gamma ray work, how does radio work, how these different properties work when we're starting to look at these cool things that are out there. So we'll see you next time.